Okay, so for A, or for example, A of 2444, notice that there's no stereochemistry for this linear compound as expected. This is going to be the diene phyl. This is going to be the diene. This is going to be a cis configuration on the top, not conformation. I've twisted things around from the conformation that was in the text to make it cis. Okay, so we're doing everything in concerted fashion, pushing electrons around, creating a cycle. We're gonna get a pair of enantiomers, right? Because this is gonna be cis and this is gonna be trans. So you're gonna see a different configuration. In other words, they're gonna be kind of like on opposing sides of one another, if you will, sort of like you would think of trans. Okay. Now you have two double bonds here. Remember, if you're working with a triple bond, only one of the pi bonds is going to reach out. So in other words, one of the axes there, or either X or Y. Okay, and then you're going to form the enantiomer of that particular product. So you're going to have a racemic mixture. In other words, if you were to flip this upside down or just rotate it 180 degrees that way, you're going to see a mirror image of what you see here on the right. Okay, and the same sort of effect is what you're going to see for B here. Now, notice that you have some electron donating groups, or at least slightly, with those methyls. Okay, again, but here on the right, you're dealing with a stereospecific trans dienophile. So in other words, there's going to be two cyano groups that are going to be trans to one another. Okay, so you're going to have an anti-configuration right here, and if you took a mirror image of that, again, you're going to get an enantiomer that's going to look like so on the right. So it's going to be enantiomeric pairs, or a racemic mixture once again. Excuse me. All right, moving on to C now. If you have a cis dienophile, and then you have a cis structure or diene, again, the same thing as you had for B. Now you're going to be establishing those cyano groups both on the same end. So in this case, they're going to be sticking out. If you had a mirror image of it, it wouldn't make any difference, because remember, there's an axis of symmetry about the product and along the center there. So that's why I drew those sort of dotted lines. So in other words, it's going to be an achiral compound with stereospecific center. So these two are stereospecific, but the overall molecule itself can't have any kind of handedness. So it's going to be a meso compound. If you need any refreshers on that, you can take a look at chapter 6. Sorry, chapter 5. Now, bicyclic compounds. So there's endo and exo stereochemistry. So there's electron withdrawing groups, and then electron donating groups are even more influential in this case. So really, to help you out, if you want to take a look at the bottom of page 1212, they have a really snazzy looking visual aid to kind of assist you with that theory. Some of you are great visual learners, some not so much, but it's a matter of just really kind of getting the principles down. Okay, so there's going to be a bridge carbon, or bridge carbons that repel the electron withdrawing groups. So think of most electron withdrawing groups as being pretty bulky and pretty substantial in size relative to the carbons that are forming the ring. Okay. So the electron withdrawing groups from the dienophile itself in particular, so those are the ones that are really forming another bridge, if you will, with an original cyclic compound. So we'll look at kinetic versus thermodynamic products. Why don't you guys take a trip over to page 1240 and look at 24.47. We'll go over some of those examples here in a minute, so pause for 5 minutes and give that a shot.